Hello everyone, welcome to lecture 8 and module 3. In the last two lectures, we have discussed about the formation properties such as elastic property of the formation and different properties of sound waves. So we know that when the transmitter inside our sonic logging tool send a sound wave inside our wellbore, it can travel through the wellbore fluid as a compressional wave or P wave. It can strikes on the walls of the formation, and there it can generate both a P head wave and a S head wave, and there could be other types of wave can also be generated, but we know that the P head wave which is generated and which is traveling alongside the walls of the formation will be the fastest wave because it has the lowest path and highest velocity. So by monitoring the arrival time or the transit time of this compressional head wave inside our formation, we can get an idea about the what is the velocity of sound wave inside our formation. So what is the compressional wave velocity in our formation? It is what we are trying to calculate from the sonic logging tool. And since the velocity of the formation is different in different medium, it depends upon the its elastic modulus as well as the density of the medium. So that means the velocity will be dependent upon the what type of formation is actually there inside our reservoir. So travel time or the interval transit time will be different in different types of formation. Since the travel time is dependent upon the formation properties, and average property of the formation will depend upon the porosity. That means how much solid is there and how much fluid component is there. So let's start today's lecture. So today we'll be discussing about the different types of tools, their working principle, how they can measure the travel time, the DOI and the vertical resolution. Can we change the DOI of our sonic logging tool to get a true porosity measurement from the formation, and different factors which can affect our tool performance. And thereafter I will introduce you to porosity calculation. So these are the some of the common sonic logging tool, such as we have a borehole compensated sonic logging tool, long space sonic logging tool, and array sonic logging tool. So these are the some Schlumberger common tool name which have been developed. Different logging company might have a different name. So before we discuss how this tool works, let us first start with the simplest explanation of sonic logging tool working principle. So a single transmitter and single receiver tool could be the simplest type of our sonic logging tool. So single transmitter, single receiver tool, they were the first generation of logging tool which were designed to measure the travel time inside the formation. So here we had only single transmitter and single receiver, and this is the distance of the sound wave travel path inside our mud, that is A. Then sound wave travel time inside the formation. So this travel path has a length of B, and this is the travel path again inside the mud. So we know that once the sound wave is emitted from the transmitter, it is traveling as a compressional wave. There it can reflect or refract, and a number of wave will be generated, but the our P head wave will be the shortest wave. So we are monitoring this P head wave which will reach the receiver first. So because the P head wave has the shortest path and it has the highest velocity, it will travel faster inside the formation and then again come back to the receiver first. Other waves will be reaching the receiver on a later time. So here it will be a P head wave. Again it will travel inside our mud as a compressional wave. So total travel time would be what? A divided by Vm, that is the velocity of sound wave inside the mud, plus B divided by V or Vf, that is the velocity of the sound wave inside our formation, plus C divided by Vm again. So here we do not have anything to eliminate the travel time inside the mud when we have only a single transmitter and single receiver. What we are interested? We are interested in the this P head wave travel time inside the formation. How much time is taken by this P head wave to travel B distance inside the formation? For that we have to eliminate these two time. So how this tool works? At time t equal to 0, when the transmitter start the sending a sound wave inside the formation, it will start the clock. So once the sound wave is generated, the clock will start, and the moment the sound wave is reaching the receiver, the clock will stop. Okay, so it will know that okay, my at t equal to t, a sound wave has reached the receiver. So that t equal to t time is nothing but this total travel time. We cannot eliminate the travel time inside the our drilling feed with the help of single transmitter and single receiver tool. That's why these tool became obsolete, and later on more advanced logging tool were developed to calculate the travel time inside the formation. Now let us discuss the next tool where we have single transmitter but two receiver. By using two receiver, we are able to eliminate the effect of our travel time inside the wellbore fluid or the borehole fluid. So here the sound wave will be emitted. First it will travel through the mud, then it will go to the formation, then it will again come back to the first receiver. Some part of the sound wave will again keep on traveling. It will go to the second receiver, and then it will again go to the reach the second receiver. So this way the sound wave can be recorded at both the receiver. So what is my total path? Let's say for receiver 1, the total travel time from receiver 1 is T1, and total travel time for receiver 2 is, let's say it is T2. So T1 will be A by Vm, that Vm is the mud velocity or the sound wave velocity inside the mud or our wellbore fluid, plus B by V, where V is the velocity of sound wave or the compressional wave, because the sound wave which is traveling inside the formation is a compressional wave. So the first arrival for which we are noting down the time, that is the always the compressional head wave which is traveling inside the formation. That's why this velocity is for what? Formation compressional velocity plus c by vm. So again c by vm, here mud time, these two are mud time. Similarly for second receiver the path will be little bit longer. So again we have travel here inside the mud, then travel here inside the formation, again inside the formation, and then again inside the wellbore fluid or the mud. So it will be travel time inside the wellbore fluid A by Vm plus E by Vm, then travel time inside our formation. Now if we subtract these two, T2 minus T1, and if the tool is inside our center of the wellbore, then A must be equal to C must be equal to E. So T2 minus T1 will be nothing but this A and C will be cancelled out from A and E, T2 minus T1, and again B by V will also be cancelled out. It will be D by V. So that means this time. So T2 minus T1, it is D by V. So T2 minus T1 is what? It is the travel time taken by the compressional sound wave to go from here to here. So what is the tool recording? It is recording the travel time inside the formation, and this travel time is equal to how much time taken by the sound wave or the compressional wave to travel a distance inside the formation, which is equal to tool spacing. So T2 minus T1 I can also write as Ls by V, where Ls is the our tool spacing. So delta T will be what? Or the transit time, interval transit time, or the slowness of the formation. It will be T2 minus T1 divided by Ls. So this we need to divide by Ls. So that will be equal to what? 1 by V. Because we are defining interval transit time as what? How much time taken by the sound wave to travel a unit distance inside the formation. That should be equal to 1 by V. That's why we need to divide the T2 minus T1 by the tool spacing. So this way interval transit time or the slowness of the formation can be computed by single transmitter and dual receiver tool, which can also eliminate the effect of our sonic wave travel time inside the mud. So this way we are getting only the true travel time inside the formation. So this is our slowness or the interval transit time, which is free of our wellbore fluid travel time effect. Now again, this tool can eliminate the effect of wellbore travel time, but only when wellbore size is uniform and tool is in center. What if tool is not in the center position? If the tool is tilted, then again it cannot calculate the travel time with good accuracy, because A is equal to C is equal to E only when tool is in center. If the tool is tilted, A will not be equal to C and C will not be equal to E. So if A is not equal to C is not equal to E, we cannot eliminate the effect of sound wave travel time inside our mud. In that case, we can use this borehole compensated sonic logging tool, which have two transmitter. One is the upper transmitter and second is the lower transmitter, and it have four set of receiver. That means one set of receiver is here R1 and R2, and second set of receiver is R3 and R4. So lower transmitter uses R1 and R2, upper transmitter uses R3 and R4. Now you can see even this tool is tilted. What will happen if you use the lower transmitter and these two receiver, and if you use the upper transmitter and these two receiver, one is going to overestimate the travel time and one is going to underestimate the travel time. So if you take the average of the travel time measured by these two set of transmitter and receivers, their average will be free of our borehole effect, borehole size effect, or the tool sound tilt effect. So this way, by using two transmitter and corresponding receiver, we can do the time averaging the travel time and get a true travel time inside our formation. So in this figure, we can see again we have lower transmitter, upper transmitter. These are travel time at different receiver. Okay. So by taking one set of transmitter and receiver into account, and by taking another set of transmitter and receiver into account, we are calculating two travel time inside the formation. When they are divided by the length, it is going to give us the our interval transit time, and we are dividing by 2 to do the averaging. Now, the depth of investigation of such tool. So generally the P head wave, which is generated upon the reflection of the compression wave at the borehole wall, is traveling inside our alongside the walls of the formation. So still the sound wave will at least penetrate some distance inside the formation, but the depth of investigation is generally very small. In general, the depth of investigation depends upon the wavelength. So what is the wavelength of sound wave? That means how much distance is there before the sound vibration repeat itself. So lambda is V by F, where V is the velocity of sound wave and F is the frequency. And the depth of investigation is approximately equal to 3 lambda. And it will also depend upon the spacing between transmitter and receiver, which we will discuss in a bit. So for a typical 20 kHz frequency of sound wave, lambda or the wavelength generally varies between the 0.25 to 1.25 feet. So dy will be around 0.75 to 3.7 feet. So what should be my transmitter to receiver spacing? Let us say this is my well bore, and this is here I have transmitter, and here I have receiver. So this is transmitter. So inside the well bore, wave is traveling with Vm, and then it is converted to a P head wave. Then again come back to the well bore and goes toward the receiver. There could also be a wave which can travel directly from transmitter to receiver. That means this is our compressional wave travel path, which will arrive at the receiver first, as we have discussed. But there could also be a wave which can directly travel inside the mud, like this. Sometimes this wave can be the first arrival. For example, if the spacing between the transmitter and receiver is very small. So let's say here. So a wave is traveling like this, then going here and here. It has so long travel path compared to a direct coupling between transmitter and receiver. So a wave which is directly traveling from transmitter to receiver, when the spacing is very low, may be detected first rather than the compressional wave which is traveling inside the formation. That means we cannot have very small spacing. So spacing between the transmitter and the near receiver should be such that it should be long enough that the first arrival are always the compressional wave arrival which is traveling inside our formation and not the mud wave, especially in slow formation. That means when the formation velocity is very slow. If the formation velocity is very slow, so the compressional wave which is traveling inside our formation, it will take a very large time to go toward the receiver. That means there should be critical spacing. That means receiver should not be kept very close to the transmitter, it should be at least at such distance such that the compressional wave which are traveling inside the formation are always the first arrival. Also, the spacing should not be very large enough, because if you have very large spacing, then the compressional wave have to travel a large distance inside the formation. The sound wave will get continuously attenuated while traveling inside the formation. So what will happen? The amplitude of the wave will decrease, the sound energy will decrease, and if the spacing is very far between transmitter and the first receiver, that sound wave will get so much attenuated that the receiver will not be able to record this compressional wave which is traveling inside the formation. That means spacing should not be very short enough, and at the same time it should not be very long enough also. So as you can see in this graph, here it is the transmitter to receiver's distance ls and transmitter to receiver time. So you can see this graph, this line is for our formation wave or the compressional wave which is traveling inside the formation, whereas this line is for our wave or the mud wave which is traveling from transmitter to receiver directly inside our whalebone. So you can see up to critical spacing, this is our mud wave have the first arrival and this is our second arrival. So this is first and this is second. After the critical spacing, our formation is the first arrival and the mud arrivals are our second arrival, because the formation will take less time after the critical spacing. So that means we must determine the critical spacing needed to ensure that the compressional wave are always the first arrival depending upon the property of our wellbore fluid and the formation. So this could be derived in this way. This critical spacing can be given as 2 multiplied by standoff. That means what is the spacing or distance between the tool and our wellbore diameter. So this is given as the d minus d by 2, where d is the hole diameter and d is our sound or the tool diameter. So critical spacing is given as 2 times standoff multiplied by under root of v plus vm, where v is the our compressional wave velocity inside formation, vm is the our compression wave velocity inside the mud, divided by v minus vm. So you can calculate critical spacing in this way. So you can see in this figure also, here what we have there in this figure, we have minimum transmitter to receiver spacing and mud to formation velocity contrast. That means vm divided by v, and this is the standoff between the hole diameter and the tool diameter. So you can pick what should be the minimum transmitter to receiver spacing between the depending upon the formation velocity and the mud velocity expected, and the depending upon the tool diameter and hole diameter. Again, this is another graph where you can see the for different borehole size what is the maximum travel time that can be measured by the tool for different spacing. So in this way, depending upon the tool spacing, we can make sure that, or we can identify how much delta t can be measured, or in what wellbore condition tool will be able to give us the formation travel time. So this way, depending upon the tool spacing and what is the condition expected inside the wellbore, that means how much standoff will be there, or what is the mud velocity or the sound wave velocity inside the mud and the sound wave velocity inside the formation expected, we can make sure that our tool will be able to record the true travel time inside our formation. So we must have a critical spacing between the transmitter and the receiver, so that we can record our true compressional wave arrival time for the wave which have traveled inside the formation. Now, vertical resolution and the tool span. So vertical resolution is the minimum depth of the formation which we can record with this tool, and the tool span is nothing but the distance between the tool receiver. So generally vertical resolution is our almost equal to the tool span for the sonic logging tool. So if you have very bad vertical resolution, you will not be able to detect the thin waves. So generally DOI and the tool span both are related. If you want high depth of investigation, you must have a larger receiver spacing. That means the spacing between two receivers must be very large. But if when you keep the spacing between the two receivers very large, obviously it is going to decrease your vertical resolution. So if you want a good vertical resolution, that our spacing between two receivers should be small. For example, in this figure, we have a 1 feet span and we have a 3 feet span. That means receiver spacing is 1 feet here and receiver spacing is 3 feet here. So both can be used. You can see in the first record and second record. Both response are almost similar, but some detail is lost when you have 3 feet spacing. You can see somewhere the thin beds are not correctly characterized by the our 3 feet span sonic logging tool. So generally most of the tools which I have seen from the published record, they have spacing at least in the borehole compensated sonic logging tool around 2 feet. But different spacing can be used if you want to have a good vertical resolution. Now, altered zone and the drilling activity effect on acoustic properties and how it can affect on our log measurement. So, due to the alteration on the formation properties, its elastic property can change, its density can change. So, the travel time of elastic wave can also change due to change in the formation properties. That means during drilling, if the formation is damaged, its property is going to change. So now it will be completely different formation with different elastic modulus and different densities. So obviously the compressional wave travel time inside the formation is also going to change. So for example, in this log, you can see we have used a borehole compensated sonic logging tool to record the interval transit time at different depth at 4 days and 80 days. So this is the record of our interval transit time or slowness of the formation at different depth inside the formation. You can see the record taken at two interval, one at 4 days and then again after 80 days are different. So obviously it indicates that the formation property have changed. For example, you might have accidentally created some fracture due to high mud pressure, or if shell is present, shell can absorb water. If you are using a water-based mud, so shell or the clay can swell, it is going to change our property. So generally the near wellbore region can get damaged due to the drilling activities. So its porosity, permeability can change, its density can change, its elasticity or elastic modulus can change, which will lead to have a different travel time than the original undisturbed formation. So beyond the formation, near wellbore region might get damaged, might get altered, but the true formation beyond the altered zone will still have the original properties. So you want to measure the properties of this unaltered or non-damaged formation, undamaged formation, because that will give you true porosity, permeability estimation of our real reservoir or undamaged reservoir, which you can use in the reservoir estimation calculation or the fluid flow calculations. So how we can handle this? So we can have a larger tool spacing, and this way we can change the depth of investigation. So due to damage by drilling activities, what can happen is that the velocity of sound in this damaged zone or this altered zone can decrease. So travel time this in altered zone will be higher than the travel time in our true formation or undamaged formation. So we know that a number of waves are generated, a number of sound waves are generated. So this is the sound wave which is quickly refracted and traveling as a head wave inside the formation, then again going back to the receiver. There are other waves are also there which can go deeper inside the formation upon refraction and then come back again. So initially this wave, our first wave, which was traveling inside the wellbore wall, it was the fastest wave. So that's why this wave was reaching the receiver first. But now here the travel time have increased or the velocity have decreased. This zone still have less travel time or high velocity. So if we want that this sound wave which is traveling deeper inside the formation can reach the detector first or the receiver first, what we have to do is we have to make sure that this travel path is long enough such that the first wave or the head wave which is traveling inside the walls of the formation alongside the wellbore wall will arrive at a later time. That can only happen if you use a long spacing detector. So by using a long spacing detector, this travel path of the sound wave are increased. So at a sufficient larger travel path, this second wave which is traveling deeper inside the formation will go back, will travel inside the formation and come back to the receiver first, compared to this my P head wave which is traveling alongside the walls of the formation. So this way we can use long spacing detector to detect the wave which is traveling much deeper inside the formation as a first arrival, so that we are measuring the properties and thus porosity in our undisturbed formation. Also, in large boreholes, mud arrival may reach first when the borehole size is very large. So by making it tool spacing very large, we are increasing the travel path of the mud wave or the sound wave which is traveling inside the mud. So again, we are making sure that the compressional wave which is traveling inside the formation is reaching first. So this way, the altered zone effect can be minimized by using a sonic logging tool which have larger spacing between two receiver and the transmitter. So the transmitter receiver spacing must be increased. So this is how this tool works. You can see here, now we have spacing between the transmitter and receiver of 8 feet or 10 feet or 12 feet. So now the spacing, earlier it was, the maximum spacing was 5 feet between the first transmitter and the farthest receiver. Now the farthest receiver will be at least 10 or 12 feet apart. Now the compensation part. Earlier the borehole compensation was done by taking average of two set of transmitter and four receiver. But if you see in this figure, we have only two transmitter and two receiver. We do not have two transmitter and four receiver. So here we have a depth derived compensation. So basically we have two transmitters which are 2 feet apart and located 8 feet below a pair of receiver that are also 2 feet apart. That means this distance is 2 feet, this distance is 8 feet, and this distance is also 2 feet. This way total tool spacing is 2 plus 8 plus 2, that is 12 feet. So what we do is that we will take the first record. So when the tool is here, we will take the first record. So what we are going to do is that we will ping the transmitter 1 and record the travel time from the receiver 1 and receiver 2 just like earlier. So this transmitter is used and we are going to record the travel time by using receiver 1 and receiver 2. When the tool will move up again after certain distance, then I will ping these both transmitters T1 and T2 and record the travel time at receiver 2. So this way again I can record the travel time by pinging the two transmitter and recording their travel time at a single receiver. So now I will have two travel times, one delta t here from the lower position, then again travel time here from the next position. This could be averaged to get the average travel time inside the formation or the interval transit time inside the formation. So you can see this will be the measurement point. One record I am taking when the tool is in this position, one record I am taking when the tool is in this position, and they both can be averaged to give us the travel time, average travel time or interval transit time inside our formation. So delta t will be the first measurement plus second measurement. So let's say first measurement travel time at two receivers are T1, T2. For second measurement travel time at the second receiver is T3 and T4. So the first measurement will be T1 minus T2, second measurement will be T4 minus T3 divided by span to give us the actual transit time for 1 feet distance and divided by 2 to get the average of these two measurements to calculate the average transit time. Since span is 2 feet, it would be 2 into 2 into 4. So this is an example of, you can see here, this is the record of long speed sonic logging tool. This is the record of our borehole compensation sonic logging tool, and you can see they could differ because the formation properties has been altered in the near wellbore region, and since the tool depth of investigation for BSC is very low, they are highly affected by our near or altered zone effect. Since in case of borehole compensated sonic logging tool, the first arrival are always the compression head wave arrival which are traveling to the our altered zone. Now altered zone will have what? High travel time and low velocity, because it could have been fractured and the fluid might be present, which will going to lower the velocity of the sound wave. So you can see the high travel times are recorded by our borehole compensated sonic logging tool, whereas the long space sonic logging tool, it is going to record our true travel time in the undisturbed zone. So this is the advantage of using a long space sonic logging tool. So you can identify where the formation has been damaged or where there is no damage have taken place. So their borehole compensated sonic logging tool and long space sonic logging tool will read the same travel time, but in other region they will show the different travel time. Now only disadvantage of using the LSS or the long space sonic logging tool is that they are prone to cycle skipping and noise. So what is cycle skipping? So cycle skipping is the presence of spike or sudden changes in the log record depicting a very high interval transit time. That means like in this figure, we are taking record like this, suddenly we are recording a very high travel time like here. So these are cycle skipping. So what happened when the sound wave travels through the formation medium? It is continuously attenuated. So amplitude of sound wave is going to decrease. We know that we set a threshold values or the cutoff amplitude value. Now you can see at the receiver, the first cycle of the sound wave, it has only this much amplitude, which is less than the our cutoff amplitude. So although sound have reached the receiver, but the receiver will not detect the arrival of the sound because the amplitude of the sound is less than the cutoff amplitude. Instead, the sound will be recorded when the next cycle of the sound wave, when it has higher amplitude than the cutoff amplitude. So this is the additional time. You can see this is the additional time due to cycle skipping. So due to attenuation, the amplitude of the sound wave have decreased. That's why the receiver was not able to record the first arrival. Instead, it is going to record the second arrival of our compressional sound wave, which is arrive at a later time. So our travel time recorded by tool will be increased. So it will happen somewhere at different depth where the this attenuation is large, and this will be present in terms of our cycle skipping. So this is pretty much present when we have a gas bearing formation on fractured formation. So in case of aerated mud or enlarged borehole, or when the fluid or when the sound have to travel through the formation fluid such as gas, or when the sound wave has to travel to the fluid in the presence of high porosity in terms of fracture, or they are traveling through the gas, the sound wave attenuation will be very high, and then you could have cycle skipping present inside our log record. Nowadays modern logging tools are designed to continuously identify the cycle skipping, and the tool data can also be corrected at the logging software by itself. So a record, an example of this cycle skipping in a real well, you can see here, suddenly we have very large, these are the average travel time, and suddenly we have very large recording of the travel time. This is nothing but a cycle skipping. So we can also identify by comparing the log response to the actual expected response. That means we know that it is a sandstone formation. So we know that what could be the expected travel time in a sandstone formation, and we are getting too large a travel time. That means it may be due to a cycle skipping. So a caustic logging tool or sonic porosity logging tool, they are prone to cycle skipping, and this cycle skipping must be corrected before using the travel time data for porosity calculation. So we can always correlate with the other log. When we have high travel time, we should not be using the high travel time directly in our porosity calculation. First, we must check with the other log data such as density log or neutron log data that this much high travel time is justified or not. So that's why the correlation with other log is always necessary, and all the logs should be explained or analyzed together to get an idea about the porosity of the formation. Now, the third type of logging tool, that is the array sonic logging tool. Here what we have, instead of having only 2 transmitter or 4 set of receiver in case of our borehole compensated sonic logging tool, here we have a number of transmitter and receiver. Like here we have, you can see a set of transmitter here, again we have 8 wideband receiver here, and again 2 receiver here, two set of receiver here. We also have a mud measurement section to determine the mud travel time. So by encountering a large number of receiver and transmitter, we can record the complete waveform, and not only the travel time of the compressional wave, we can also measure the travel time of shear wave or Stoney wave or the Rayleigh wave also. So by analyzing a number of waves, by recording the complete waveform and analyzing all the travel time of different types of wave, we can get an idea about the a number of mechanical property of the formation. For example, we already know that the velocity of sound wave is related to elastic modulus and the density of the formation. So these record obtained from the array sonic logging tool can be used to calculate our VP, the compressional wave travel time or sonic wave travel time or other type of wave travel times, as well as the elastic modulus, shear modulus or the bulk modulus, as well as the Poisson ratio. So this way the sonic logging tool are also used apart from the Porosity calculation for estimation of a number of mechanical properties of the formation. For example, P wave travel time and S wave travel time are used in the seismology. We can determine where our center of earth K. So sonic logging tool have a number of other application also. It has application in the Porosity as well as the mechanical property of our formation estimation. It can also be used to determine the cement bond quality also. So in our course, we are only limited to the Porosity calculation because of the time constraint. We'll not be discussing the other application of sonic logging tool. We are only focusing on our Porosity measurement. That's why I have given you an idea about the elastic property of the medium so that you can understand that the travel time is related to our elastic properties and the physical property of the medium. So if you are interested in the other application, you can refer to the different books also, or you can search different literature on the internet. So today we discuss about the different types of Porosity logging tool, how do they work, what are the difference between the different type of Porosity logging tool, what are the factor can affect our Porosity logging tool response or the sonic logging tool response. In the next class, we'll discuss how to calculate the Porosity of the formation using the tool data, that is the travel time or the interval transit time or the slowness of the formation. See you in the next lecture.